interesting sites on memory locations and addresses. This session is a part of module 1. It's part B. How do we understand the memory locations and addresses? So let us look at these concepts, how to represent the memory representation and location of them. Okay. So what does this memory representation actually mean? So we all know that, let us see some examples. You all know that 1K of memory. So 1K, which means 2 power 10, correct? Which gives you 1024 memory locations. Similarly, 2K is 2 power 11, 4K 2 power 12, 8K 2 power 13, 16 2 power 14, 32K 2 power 15, 64K 2 power 16 lines. So which means the number of lines in the address is going to decide the memory capacity. Okay. So you can do one thing. If it is 2 power 16, what is the memory capacity? You can put that in your chat box so that we can able to see the responses. All right. So let us see the location of memories and how they are stored here. Before we discuss about this diagram, let us have an overview of the memory. So usually the computers will start storing the data. All right. So this computer will store the data in the form of instructions in the memory. Okay. Once we store the data in the form of instructions in the memory, this data can be in the form of numbers or characters. Either it's numbers or it's on characters. Okay. So this memory will consist of many millions of storage cells. It has a lot of storage cells, in fact. Each cell is having a capacity of storing a single bit number. Each cell is having capacity of storing single bit number. It's a 1-bit binary number. Correct? It's a single bit number it can store. Okay. And after that, the single bit representation is very small. This means 1 bit of information we cannot able to find anything, one small bit. For this corresponding reason, what we do is the memory is organized so that uh, the group of n bits can be stored or retrieved in a single basic information. So each group of this n bits is referred to as a word of information, and n is called the word length. All right. Now let us spot it out now here. Looking at this diagram, we can able to say that the number of arrays in m number of n bytes of each word can able to represent by unique address. So if you have 2 power 16 lines, we can able to represent by 65,536 memories. So that's the number of capacity what the memory will have. If it is 1K, we have a number starting from 0 to 1024. So let us look at this diagram here. Let us have the view of this complete memory words what we have. So if you see this diagram here, it's n bits length, which means it can be 8-bit, 16-bit, 32-bit, whatever. So which will have a partitions to store single bit of data. So this is the first word, second word, it will go up to ith word and last word. So this is the memory block. Okay. Whereas this n, small n, represents the length of the word. Okay. So as we discussed already, this memory will have a larger amount of storage cells. Each cell will store one single bit, and the data usually is accessed in n bit length. If it is 8 bits, we're going to access in n bits. If it is n value is 4, we can take 4 bits at one point of time. If the n value is 8, we take n bits at same point of time. Okay. So depending on that. Now you see this typical example. If the bit length is 32 bit, if it is 32 bit, we are unable to transmit that data in 32 bits in a single shot, or you can able to take it 16 and 16 in 2 different slots. All right. Now look at this binary representation. The representation of this is B0 and B1 starts with, and it keeps going up to Bn-2 and Bn-1. So n-1, n value is 32, n-1 will be 31, n-2 will be 30. So in this way we can able to do that. So this last bit is going to represent the sign bit. So this last bit is going to represent the sign bit. If that is 0, it's a positive number. If that's a 1, it's a negative number. So this is how we can able to represent the signed integer. Okay. And we have example for encoding information, 32-bit information. We can also do that if you are trying to store a character. Before we are trying to see how to do a number. Because as we know already that in memory we can able to represent either a number or a character. In case if it's a character, okay, we have here 8 bits, 8 bits, 8 bits, and 8 bits. So 8 into 4 will lead to 32-bit. So 32-bit word length can have 4 ASCII character storage capacity, and 32-bit word length can have 32 binary bit information capacity, out of which one of them in the MSB is used for signed number. Then remaining 31 bits will be used for storing the. Okay, as we have seen in the initial stage of the class, 1K will give you 2 power 10. And we all have nowadays 1 terabyte of hard disk, which means 2 power 40. So the address lines required to access this 1 terabyte of hard disk is 2 power 40. Whereas if you want to address 1 kilobyte, we can have 2 power 10 address lines is good enough. Okay. What about 16? If it is 2 power 16 address lines are required, we can able to have 64K, right? So that's why when you see any microcontrollers with 16-bit, it can have a memory capacity of 64K, and it will have the blocks in terms of 64K multiples. Okay, so if you want to have a 1 terabyte of space, we need to have 40 address lines. The 40 number of address lines is what is going to decide the capacity of memory. If you keep increasing the capacity of memory, the capacity of address lines also has to be increased. So we can have an overview of 24-bit how it is, 32-bit how it is, and all that. And we have operating systems of 32-bit. Say for example, 32-bit operating system can support you up to 4 GB of memory in terms of RAM capacity. If we talk about, so when the RAM capacity is increased from 4 GB to 6 GB, 8 GB, and so on, the operating system bit capacity also has to increase. So it went up to 64. Who knows, we may get 128-bit operating systems even in future, so that the memory capacity can be further improved upon, right? So this way it goes on with and the next session we're going to discuss more on byte addressability and bit addressability. So thank you uh, for listening. Let us meet in the next session. Thank you.